So Anisha Keshavan is a senior data scientist at a company called Octave Bioscience, and she'll tell us a little bit about the work she does there. And Anisha, before she went to Octave Bioscience, she got her PhD in bioengineering in the UCSF Berkeley Joint Bioengineering program, and did at that point an analysis of MRI data, a lot of sort of clinically oriented data analysis in MRI. And during the time that she was a PhD student, she picked up a lot of interesting skills in data science. And then after her PhD, she came and did a postdoc with myself and with Jason Yitman at the University of Washington, and did some extraordinary work, really phenomenal work on that combined a lot of interesting things, sort of both data analysis and crowdsourcing of analysis, or using citizen scientists to do quality assurance in large data sets, solving some really thorny problems that we have with these large data sets. And today she'll talk a little bit maybe about this trajectory that she's made and where she is now, and the kind of work that she does in industry with those things that she learned during her academic training and research career. Take it away.
Cool, yeah. So the name of my talk is High Stakes Neuroimaging, and it's about my transition to translational medicine and industry. And I'm currently a senior data scientist at Octave Bioscience, which is a startup. And I was employee number 15, so it's been a really fun ride. Before getting into talk, I just want to talk about what translational neuroimaging and what I mean by that. So what I mean by that is, can neuroimaging research be used to directly improve the lives of patients with neurological or psychiatric disorders? And we think of traditional neuroimaging, what we usually do is we collect a cohort of people, we get their brain MRI scans, we have a very specific question that we want to answer. So we extract maybe T1 brain volumes, maybe we do some diffusion weighted imaging, some fMRI, maybe we find a way to combine all of these metrics into some, super multimodal metric, and then we run some sort of inference, and this hopefully tells us something new about the brain. And this is great, but with translational neuroimaging, we want to do something a little bit different, which is for a single patient, can we still extract those same neuroimaging metrics and then use that as a recommendation for a doctor who could say something like, based on your MRI and this metric that we've extracted from your brain MRI, I'm recommending this drug. And so of course, traditional neuroimaging guides this translation, but actually implementing this can be really tricky. And this is what I learned in my PhD and my postdoc, and even now. So why is it so tricky? Well, at the end of the day, it's really high stakes. So for traditional neuroimaging, our data is acquired to answer a very specific set of questions. And we're very careful about how we collect this data. We're very precise. It's usually a smaller data set simply because we want to make sure it's the absolute best quality that we can get. And it's a very carefully selected cohort. You don't want to introduce all this bias into your data. You want to make sure you're balanced in many different ways. On the other hand, for translational neuroimaging, the data has to be acquired from anywhere, because ideally we want to maximize the number of people that we can help. So we don't necessarily have control over the imaging parameters or the type of MRI scanner, because we want to help people all over the country. Data analysis in a research setting is kind of like the wild, wild west. There's no real restrictions, and at the end of the day, when you're a PhD student, it's on you to push this analysis through and to write the paper. On the other hand, when you're working for a company and you're providing this service to a bunch of people, there are regulations, right? We do have an FDA. And part of this is that if your analysis isn't reproducible, it doesn't actually count. It has to be also cost and computationally efficient. And it's fundamentally collaborative, because people take vacations. I'm pregnant right now, so I'm going to go on maternity leave for 3 months. And the rest of my colleagues need to be able to step in when I'm not there so they can push data through, right? The end product for traditional neuroimaging is a publication. And it's a verbal description of the methods you used in your interpretation. But the end product for translational neuroimaging is this consistent and reliable product or service for a doctor. So what works what you provided to the doctor and patient a year ago needs to work a year from now, 2 years from now, 3 years from now. So it's very long term. And this, brings up the timeline where a PhD or postdoc timeline, 4 to 6 years for a PhD project. So that's your scope. Postdoc, maybe even shorter, 1 to 3 years. And an NIH grant, maybe 5 years. But the timeline in translational neuroimaging in industry is as long as possible. And we want to continue improving and iterating the product as a team. So you have to think of like super, super long term for translational medicine. And the scariest part for me is the mistakes. So in a traditional neuroimaging, academic path, when you make a mistake, you have to retract your paper. This might throw off the field depending on, how impactful and big it was. It might affect your career, and maybe it'll indirectly hurt someone. But a mistake in translational neuroimaging could directly hurt or kill someone. And I'm not trying to be dramatic here, but it is the reality of medicine, right? If someone is going to make a decision about what drug a patient should take based on an MRI scan and the numbers extracted from it, you don't want to make a mistake. So this talk is about my, transition. So I'm going to talk really quickly about my background, my PhD research, and what I did as a postdoc. And then I want to explain what I do at Octave, the mission of the company, and how we use neuroimaging at Octave. And then I want to touch upon the skill set for this transition because it aligns very well with basically everything that NeuroHackademy is teaching. So my PhD was focused on the mysteries of multiple sclerosis. MS is this autoimmune demyelinating neurological disorder that affects the motor, sensory, vision, all the systems basically. There are 2 main disease courses in MS, relapse remitting and progressive. So on this picture on the right here, relapse remitting is the more common type where you go for a few months and you're fine. And then there's a flare up of your symptoms. And then you come back almost to normal a couple months. And so here and there, you have these flare ups, these relapses. The other type of MS is progressive MS. So it could either just be this type, primary progressive, where you just continually get worse over a short period of time, and you're in a wheelchair within 10 years of your diagnosis, and this is really scary. What's more common is secondary progressive, where it starts out as relapse remitting, but at some point, it becomes progressive. And the biggest mystery in MS is we can't predict this disease course. When you first come into the office, we can't tell if you're at high risk for primary progressive or if you have the relapse remitting type. And even when you do have relapse remitting, we don't know when it's going to turn into secondary progressive. And this is really scary, for a patient and also for a doctor, because if you have the progressive form of the disease, then you can treat it with these really intense cancer drugs, basically, that they compromise the immune system, and you could risk dementia. I mean, it's really serious, but on the other hand, you have the ability to walk and, keep your vision. So it's really important to somehow figure out maybe who's at high risk for progressive MS. And again, if you are relapsing, at what point do you say, maybe this relapse isn't a relapse, maybe it's time to go with the more serious drugs? So you could go up, you could go back down, and you just can't tell. So my specific focus was an MRI, and the question was, can MRI predict MS disease course? And we know MRI is already a crucial part of MS diagnosis. You can see these hallmark lesions that in this case, coming from the ventricles here that are bright on the flare. In the T1, it looks like a black hole. So the white matter is now dark. And this signifies axonal loss. But what we also see is whole brain atrophy. So what I'm showing here is a pretty extreme example where this was a patient, 60s, and then 2 years later, the lesions have just combined with the ventricles, and you've lost a bunch of gray matter and white matter here. Here's an example of what progressive versus relapse remitting looks like on a T1. So on the left is a relapse remitting patient, looks pretty normal to me. There's some white matter, gray matter, what we're used to seeing. But on the right, you see these black holes. And this, very rarely, I don't know if it ever gets better, right? And so with each relapse, you're risking, damage that can't be undone in the brain. So MS also has this characteristic lesion distribution pattern. So I'm gonna just fast forward through this movie. So you can see that these ventricles kind of follow these lesions follow the shape of the ventricles, but you could also get them in the brainstem, for example, and this would probably affect your ability to walk. Not ideal. So at UCSF, we had this study called the EPIC study, and it had started way before I joined as a PhD student. And they were studying 500 patients where they acquired the MRI at their baseline, did a full clinical genetic workup, everything that you could think of. And then every year they got another MRI scan. So 12 years of MRI scans for 500 patients. Not only the T1, but T2 in the early years, then upgraded things, started acquiring FLAIR, fMRI, and diffusion weighted imaging. There were scanner and sequence upgrades throughout because, of course, you want to do what's best for the patient. So if that means upgrading your scanner so that you can see the lesions better, you should do it. And so I was like, oh my God, there are over 5,000 scans. This is such a rich data set. It's a little messy, with the scanner upgrades and everything, but there's so much potential here, right? And so I started off as young Luke Skywalker, no wrinkles, no gray hair. I was like, oh my God, I can write a for loop, we'll get through this data. And then what happened by the end of my PhD is there was just so much data, and how do you make sense of it, right? And so the specific thing that really trips me up, and it still trips me up, is that measurements on images come from visual inspection by clinical experts, and they don't scale well, right? Because not anyone can just look through an MRI scan and be like, oh yeah, there are 10 lesions here. It has to be a trained neuroradiologist, right, with a lot of experience. And so the problem that I tackled, in my PhD and my postdoc, and what I'm still working on now, is scaling visual inspection. So here's an example of, one of the scans from my PhD. And there's this juxtacortical lesion right here. And I ran it through FreeSurfer, and FreeSurfer decided that it wasn't brain. And I'm like, great, now the measurement of this region is not accurate. And this happened for all 5,000 scans. In some places where there was a lesion, you couldn't segment, the structures of the brain correctly. So it was really important to identify those lesions as accurately as we could. And so the solution here was to work with medical doctors and build an app to segment lesions. So why build an app? And specifically, I built a web app. And why did I build a web app? And why did I learn this skill, JavaScript, so I could do this? And it was because a lot of the image segmentation, software for lesions, you have to navigate bash. You have to CD to the right folder, open it up, and then make sure you save the file in a certain way so that my code could pick it up, and fix the. And it's just too much for a doctor to have to learn, right? It's not that necessary, but if you could just give a doctor a URL, say, hey man, can you find the lesions for me real quick? That is actually a lot more efficient for everyone. So, in this example, our neuroradiologist just marks the center of a lesion, marks it as a lesion, hits save, and then this goes to a database and launches a process that grows the lesion and then fills it in, and then we can run FreeSurfer, for example. And so through this process, which was kind of a mix of my work plus a neuroradiologist annotating, we were able to get through 400 scans in a month. So we could do 400 lesion segmentations a month, which for any of you who work on this kind of stuff is incredibly fast. And so this app was called Mind Control. And so I just think this is funny. So after very careful, efficient editing, we make sure that all of the brain metrics are solid. These are the best measurements that we can get from our, 5,000 MRI scans. At the same time, another neuroradiologist was going through and measuring the cervical cord. So, looking at the spinal cord and the area of the spinal cord. And when you put all of these metrics together and say, hey, can we predict who converts to secondary progressive based on these imaging measurements, the spinal cord just takes all the glory. So that's reality, is you can do all of this work and get the best measurements possible. But, the research doesn't always work out, and that's fine because now we know this. So this was a huge effort, very collaborative. There's a lot of MDs here, but also PhD students. So it was fun work. But I wanted to move on to my postdoc after this. I still wanted to work on tackling these problems of scale. And in general, you know, many aspects of neuroimaging research need visual inspection. Even if you're not carefully segmenting MS lesions, even if you're working with a completely healthy controlled data set, you do need to look at your images before you do any sort of analysis on them, right? And as you start to collect larger and larger data sets, this becomes harder and harder to do. So in the traditional research sense, when you collect bad quality data, maybe your head coil was acting up or your patient was moving, bad data generally leads to bad quality measurements, and then this leads to bad inference, bad science. But again, in translational neuroimaging, bad data means bad measurements, and this could actually hurt someone because if you don't look at the original data going into your segmentation algorithm and the segmentation is off, and we overestimate the number of lesions someone has, and because of that, it means that they're going on a pretty severe treatment, that again is not good. So for my postdoc, I worked with the Healthy Brain Network data set. And this was from the Child Mind Institute. And their goal was to study pediatric mental health by collecting MRI scans and up to 10,000 MRI scans of kids. And the question was, can we scale just visual inspection of the raw data itself, not even the segmentation, we're not going complicated, just basic raw data. And can we train an algorithm to triage these cases? Because, you know, when you get up to 10,000 scans, maybe you want to be efficient about the way that you QC. Maybe you want to QC the ones that are really borderline first and have an algorithm say, no, I'm pretty sure this particular scan is good, this one is bad, but there's a middle region where we'd want to visually inspect. So rather than, I did actually spin up my PhD work of mind control and ask people on Twitter to help me QC these scans where you'd look through every single slice in 3D and every angle, and then you would give it a rating. And the reality was it was just kind of slow. And so I thought, let's try something new. We really need to find a way to efficiently label this data as quick as possible. So I made this app called Brainder, which was a play on Tinder. And I said, are you at work but feel like playing Tinder? Why not play Brainder instead and help neuroscientists rate the quality of brain images? Swipe left to fail bad quality images. And this was built in JavaScript. So two technologies, Vue.js and Firebase. And it was a citizen science project. And this, I maybe had tens of followers before, but my tweet went viral. Proudest social media moment in my life. We got, you know, a lot of retweets and likes. And so a lot of people logged on to play Brainder. The instructions were pretty simple. If you see something with a lot of motion artifacts, because these are children, this is what we're expecting, swipe left. And if you see an image with good contrast, good SNR, swipe right. And I thought I would make it a little fun. So we added some virtual prizes. So depending on how many points you got on Brainder, you get a point per swipe, basically. You could unlock these mystery creatures. The reaction from the experts was great. Pierre Balek is one of the instructors for NeuroHackademy, and he apparently, you know, was at a bar having a beer and he was playing Brainder. So I got him to play. There are actually a lot of people that played. One guy, I don't really know who he is. I think his name is Mike. He did 6,000 swipes on Brainder, which is pretty cool. Overall, each image got, you know, 20 ratings per image. It's actually much higher now. But often there was no agreement. So as the tweet went viral, we started noticing in our distribution of average ratings, where 1 is a pass and 0 is a fail, we started noticing that this peak of our distribution was moving to the right, which basically meant that people were swiping right all the time because they were maybe too nervous to fail something. I'm not sure. So the question was, how do we aggregate these, you know, many unreliable ratings? And so we needed a model to downweight some of the raters that were swiping right too much. And so the way we did this was we created this matrix where image ID was the rows and each rater was their own column or feature. And we actually had a few experts rate a subset of this data using the traditional mind control like 3D QC. And we needed some sort of model that handled missing data, because you can imagine not everybody did 6,000 swipes, that'd be crazy. So we needed a model that could handle this missing data and figure out which raters are more reliable than others, and then give us like a final score for the image. And so we use this algorithm called XGBoost, which conveniently gives a rater importance score. And when you look at the number of ratings in the gold standard that these raters did versus their importance, we could easily pick out people that, they rated a lot, but their quality of rating wasn't very good. And so once we, aggregated and corrected these ratings, we saw a distribution for image quality that we expected, which was the majority of these images pass. There's a lot that just kind of fail outright. And then there's, this area in the middle where we'd probably want to triage. And so this XGBoost aggregation model did quite well on the held out data. And so the last step was to train a model to triage this QC. So we want to go from raw image slice to some sort of probability score. How probable is this image of passing quality control? And we did this using this neural network called VGG16. So if you know of the deep learning literature, VGG16 was this model, this really large network that was trained to identify cats and dogs and bikes from this large ImageNet data set. And what you do is if you take that final layer of the network and you retrain it on brain images, you can actually do a pretty good job. And so this ROC curve here, when we used the labels from Brander, the corrected labels from Brander, and we trained VGG16, our area under the curve was 0.99. So it basically matched experts, which was really promising. So the summary here is that when you combine the strengths of humans and computers, we can overcome some of the problems of scale in neuroimaging for both traditional research, but also for translational research. And this, at the end of the day, results in good quality measurements, which is what we really need to minimize and avoid mistakes in our research and our translational research. So that kind of transitions nicely to Octave, which is the company that I started working at after my postdoc. I want to take a step back and talk about MS in a larger context, which is that almost 1 million people in America have MS. It strikes early in the late 20s, and you live a full life with MS. You don't die from MS anymore because we have so many therapies. However, it's really expensive. So we're talking about $2 to $4 million just to treat MS in your lifetime, even if you have health insurance. The likelihood of progressing is 50%, but we don't know exactly when that transition is going to happen. And while there are so many therapies coming out every year, they're only about 30% effective. And it's a top 5 drug spend. So because you spend more than cancer because you're using these cancer drugs for much longer. So let's see. So Octave, we really want, our #1 goal is to improve measurement and management tools so that we can improve outcomes for these patients. And one way we can do this is by providing physicians with better measurement tools and better management tools, so they can feel a little more confident about prescribing, some of these more scary therapies. The payers are insurance companies, and they're happier if the patients are doing better. And pharma also is happy because they can figure out why their drugs maybe work on some population of MS, but not others. So they can work on building more effective drugs as well. And so Octave has many goals. We're not solely a neuroimaging company. The main goal is we want to delay disease progression. And so one way to do that is to delay relapses. And why are people relapsing? Well, it turns out that some of these drugs aren't simple pills, but they're injections. And maybe if you're feeling okay, you want to avoid an injection. But it turns out when you avoid your treatment, this could make you more likely to have a relapse. So we built an app to remind and track treatment for these patients. But that's not the full story, because we also want to avoid hospitalizations. And hospitalizations, you can imagine, are very expensive. And now in the time of COVID, you really, really want to avoid going to the hospital. And so what we do is we have this care provider that checks in with our patients every 2 weeks. And, maybe a patient is saying, oh, I feel a little weird, maybe my motor abilities aren't as good as they were. Is it worth going into a clinic right now? And she can decide whether it's worth it or not. And this is really important because some of our patients are like 2 hours away from the nearest neurology clinic. So you don't want to wait too long until it's so bad that you have to be hospitalized. You want someone to say, oh, you should go in now. We also want a way to quickly measure inflammatory markers to track this disease. So while MRI is really great, it's really expensive. And again, you have to like physically go to an imaging scanning center. But ideally, there would be some sort of blood test to measure these inflammatory markers, and they could tell us how your disease is progressing. We also want a way to monitor patients in between visits so that we could maybe predict these relapses a little better. And so we're going to start up a sensors and wearables program to track mobility and sleep and everything. We want to use all of this data in combination to predict worsening of any sort. And so we have a data science team that we're still always looking for new talent. And then the part where I come in is we want to provide these neuroradiologist reads for MRI with quantitative information. So not just, okay, this patient has MS, but how many lesions does this patient have? And this is where our neuroradiologist plus our translational neuroimaging team comes into play. So what do we do? So before Octave started, our founders did a lot of market research, and they asked neurologists, like, what do you want out of an MRI report? What could make it more effective for you? So community neurologists, don't have access to a specialized neuroradiologist all the time. And when I say community neurologists, I mean people that aren't necessarily at like UCSF or like, you know, a big research institution, but people that are in the community. So what we do at Octave is provide them access to a neuroradiologist. Another complaint is that MRI reporting is not consistent. So sometimes, you know, you have your patient go to a scanning center and it's going to be read by a different radiologist or neuroradiologist each time. And the way that report is structured is going to be different. And this is hard to really compare between time points, like the changes that happened over time. So we provide a structured report. And then our neurologist told us that quantitative features over time would be really valuable. So examples of this are the number of lesions that a patient has, lesion growth or maybe shrinkage, lesion maps, so if they could actually see where the lesions are, and then measurements of brain atrophy, because this is also signature MS. They find it would be very valuable, but we come back to the original problem that I encountered in my PhD, is that, you know, when we want to report brain volumes, atrophy, and lesion counts, and we do this by running this data through FDA-approved software, but we don't want to risk any mistakes. So I brought Brander into my company. We wanted to ensure that our quantitative metrics are accurate. And we have a neuroradiologist who will verify segmentation accuracy before writing a report. So that's good. But we need to make sure that he doesn't waste his time editing segmentations, because this, again, can't scale. And we want to scale because we want to help as many people as possible. So what we have is a variant of the same Brander app where we highlight a lesion segmentation and you swipe right if it looks good and you swipe left if it looks bad. And so everyone in our company is playing this. And similar to what we saw with the original version of Brander, there are people who haven't seen like brain images or lesions before that have gotten better and are actually, their ratings are pretty valuable. So we're working on incorporating Brander into this kind of flow where when we run data through an algorithm, we also have a really quick way of QCing it so our neuroradiologist isn't completely overwhelmed with all the data that we have. So future goals, after we get this, you know, flow in place and we have a large number of really solid measurements of the brain, there's a lot of really cool things we can do. So one thing that we want to do is build kind of these interactive data visualization dashboards, because I'm sure all of you have experienced when you can collect so many different types of imaging features, really high dimensional data. How do you actually make sense of it? And so the first step usually is data visualization. We also believe that these visualization can engage and educate patients. So here you can see the actual distribution of lesions. Like maybe this is why you have to take your medicines on time, right? And then we also want to combine this MR data with our blood-based biomarkers and our sensor and wearable data, and use this to prevent and predict worsening in our patients, and then eventually make treatment recommendations. So a lot of really exciting stuff to make a difference in people's lives. So I want to talk about this kind of translational skill set that I picked up along the way. Reproducibility is mandatory for translational neuroimaging. I mean, if for some reason we couldn't replicate the process that we use to extract metrics for a given patient, the whole thing falls apart, right? And so how do you get better at reproducibility? Well, learning Docker is a really good first pass. So having some sort of consistent organizational structure for your data long-term is a good idea. And so that's why I think BIDS is really important. I organize our neuroimaging data at Octave in the BIDS format. Version control is crucial because sometimes you have a mistake in your code. You want to go back in time a little bit and fix it up. And then in general, it's important to be able to code because we can't point and click our way through analyses when we want to scale. And I think it's very important to understand concepts so that you're able to pick up new languages. So JavaScript isn't something that is a traditionally like taught for scientific research, but I picked it up because I needed to work with doctors. And so being able to pick up new languages is a very useful skill. Again, cost and time efficiency really matters because healthcare in America, at least, is already insanely expensive. So we don't want to add even more cost to their healthcare. And so this matters when you're deciding, should I learn Python when I already know MATLAB? When it comes to industry, Python is free, but MATLAB isn't. So it might be a good idea to, learn some more free languages. And then also knowing how to write workflows and working with distributed computing is really important. So NiPipe is something that I also use. And this, again, because we want time efficiency here. Cloud computing, I am on AWS every day. It's still something that I'm learning. It's really complicated, but it's, again, worth learning and worth putting some time into. So we use AWS at work, but in my postdoc, I was working with Google Cloud and Azure as well. And then, like I said before, collaboration is key for long-term resiliency of your software. And again, Git and version control really helps with this because you can work with people. And then, of course, data visualization is really important for communication. And I'm not just talking about communication with other scientists in your company, but communicating with your CEO or the head of marketing or something like that. It's really important to work on those skills. And then, of course, you need to be strong in statistics and machine learning because data can very easily mislead you and you need to be very careful. When I was getting my PhD, it was always this battle between, should I learn these new skills that I think I probably need that would probably make my science efficient in the long run versus should I be reading these papers? Should I be, writing a paper? And it's always this careful balance between, learning all these new skills that will help you in the long run versus doing what, you need to do to get your degree quickly. But I think all of this was worth it for me in the end. So I'm going to conclude here so that you all can ask me questions, but I just want to touch on something that my engineering professor, our first engineering class, I got my degree in aerospace engineering and I was taking this class on like bridges and statics. And he said, a doctor only kills one person at a time, but an engineer is able to kill hundreds if they build a faulty bridge, right? And I think this is really important because as we're bringing AI and, machine learning into traditional medicine, we're trying to merge it and make it translational. We run the risk of building a bridge where biases in our algorithm or mistakes in our algorithm can start to scale and hurt a lot of people at once. And this is really scary. But it also, we have so much potential to improve so many people's lives, so we just have to be careful. And so I'm happy to take your questions. And if Octave sounds cool to you, please contact me. Feel free to email me or add me on LinkedIn. That is a thing that industry people use. So, that concludes my talk.
Thank you, Anisha. That was really great. Let's see if there are any questions. You can type those into the Q&A interface on Zoom and ask. I'm kind of wondering, one thing that sort of is on my mind when I see all this is I see this transition into industry. I wonder, so the thing that comes to mind is this concept of augmented intelligence instead of artificial intelligence, right? So you have this machine proposing something, and you can really accelerate things.
Yeah.
So how do you think about it? Do you think this is what we're going to do now? Is augmented intelligence for a long while, or is it going to be eventually artificial intelligence taking over?
I'm scared of computers taking over 100%. I mean, we've all seen the types of segmentation mistakes that a computer makes that a human being would never, ever do. So the way I think about it is, I think augmentation is key for translation in general. I mean, we have our neuroradiologist check everything before he writes up a report. So in any way that we can make him more efficient, I think he would be happy, and then our company would be happy because we could help more people. without.
And then you can't help but wonder, how is the next generation of neuroradiologists going to get good at this
Yeah.
if they have these machines helping them?
Yeah, I mean, it is weird, right? And we've seen it with, we've seen like kind of disasters when it comes with autopilots. And again, my undergrad degree was in aerospace engineering, so this is the analogy I'm going to make. But you know, when we first had airplanes, the pilot had to do everything. But now, you know, all parts of the plane are kind of like, you know, the flaps and everything. It's all kind of automated. So why do we need pilots? Well, there are times where it really does matter, you know, and we've seen like catastrophic things where, you know, mistakes in kind of the measurements of all these systems make the airplane go higher and higher. And then if a pilot doesn't recognize this problem, then the plane stalls and falls. So I think it is very important that neuroradiologists still have their traditional training and can watch out for mistakes. Yeah.
Of course, yeah.
Yeah.
Okay, there's a question in the Q&A. Luke asks, he says, great talk, Anisha, first of all. If you're going through training again, what experiences do you recognize you missed or weren't available that you wish you had to make you successful in the industry environment?
That's a great question. I regret not doing an internship in industry. I wish I had known what it was like going into it. I think my job right now, it aligns so well with what I was doing. I mean, it aligns perfectly with what I was doing in my PhD and postdoc, but I also, yeah, I think I'm curious to know how other industries worked. And I had a pretty closed mind going into, you know, my interviews for industry. I was like, I don't know, these people just want to make a bunch of money. Like they don't care about helping people, but that's like completely opposite of reality. I mean, everyone in my company really cares about helping people. And so I wish I'd given industry more of a chance.
Great, yeah, and internships, I hear you. I think that's a really great idea to take opportunities to do internships. It's not as common in, I'd say, in neuroscience departments.
Neuroscience, but because we're starting to incorporate, you know, machines in our research, I think it's starting, you know, we're starting to become more like engineering, and engineering, I think, generally has more internships. Yeah.
So I'll give another chance for people to ask questions. Okay, I see no more questions appearing here, but we'll have a page for this on NeuroStars, and people can go and ask questions there. And Anisha's on NeuroStars all the time. Oh, hang on, there is a question. Allison says, really cool talk. What was your process for picking up these skills? When you were selecting the projects you worked on during your PhD and postdoc, did you select them to build these skills, or were they just by happenstance? And I'm giggling because I know how these things happen. So go ahead.
Oh, I wish maybe it seemed like I had the plan the whole time, but no, it was complete happenstance. I thought I could walk in to this massive, you know, MS data set and just run all these segmentation algorithms and like do some cool machine learning on the output and find these patterns. But that wasn't the case at all, right? So it was more about, I picked the project because I thought it had a lot of potential. And then I realized that actually there were a lot of like random things that I didn't know that if I could learn, I could actually make this process, you know, more efficient.
Yeah, I think different people gravitate towards different aspects of very large, complicated problems.
Yeah, yeah.
You know, what is it? The serendipity and the favoring of prepared minds, right? Your mind was sort of prepared to take the happenstance of something that showed up in your data or in your situation that you could go with. So I think there's
yeah, I was just like, oh man, like I really wish this neuroradiologist would work with me more. How can I make this more enticing? Oh, maybe I should just like pick up this JavaScript skill set so it's easier to work with people. Yeah.
Right, and I think part of what you talked about, I think is an important part, is to recognize that things that seem like dead ends, like, oh, okay, we're sort of stuck here, don't necessarily have to be dead ends.
Sure.
Provided you're willing to sacrifice short-term
certain things, yeah.
Short-term kind of finishing the project for long-term learning the skills and so on. So there's a, like you said, there's a balance.
Yeah.
Okay, great. Okay, one more question. There are more questions coming, so good. So thanks for sharing your journey. Can you explain again why non-radiologists' evaluations of brain are still valuable for the analysis?
Yeah, again, it's because computers make these kind of like really weird mistakes, like crazy mistakes that a human being, like even a normal like non-neuroradiologist human being can answer. I mean, we're talking about just like very obvious mistakes, and there's no need for a neuroradiologist to be like, why would I even, like, how is that even possible, right? But for, you know, people like you and me, or people who've never seen brain scans, sometimes it's very obvious when a computer has mistakenly traced something. And so if we could get rid of all of those super easy problems for the neuroradiologist, he only has to, or she, in our case, his name is Mike, so Mike only has to worry about those tricky cases, and that's what he's really good at. So if we could just find a way to only give him the tricky cases, that is the most time efficient use. Yeah.
Okay, one more question. Thanks for the really interesting talk. Can you provide some suggestions on keeping the balance between research and engineering work that you have to do?
Yeah.
And I'll add, did that balance between engineering and research kind of shift when you went from an academic environment into Octave?
Yeah, it's hard is the first thing I had to say. And you really have to, I mean, there's so many things you could do to make your research more reproducible, right? I mean, everything you do could have its own Docker image. You could comment your code extremely thoroughly. You could have tests for every single function that you write, but then you're never going to write your paper, right? Like you're never going to get there. And, but you'll have really good reproducible science. So it is a balance. I don't know if I have a good strategy other than I try to make timelines for myself that are a little more lenient than maybe other PhD students. Give myself a little bit more time so I can, but not so much time that I'm taking, 10 years for my degree. Yeah, I'm sorry, I don't have a better strategy, just that something to keep in mind.
Yeah, I think for me, also just, sorry, I'm still in your microphone here, but I think spending time with your with your colleagues who have different inclinations. If you are like me, and I guess like Anisha as well, drawn into engineering projects, spending time with your colleagues who are less engineering inclined is a good way to sort of get a reality check on
Yeah, definitely.
and stay curious about other things as well. Because I think part of my draw into engineering has to do with sort of this kind of becoming a little bit kind of lost in the research side of things and kind of disenchanted maybe with research questions. So if that's the problem, then getting re-enchanted can happen through other people as well.
Yeah, definitely a good idea to get re-enchanted. And the environment that I was in at UCSF, there were doctors all around me talking about, their patients. And so this kind of brought me back to reality, like, okay, we have to help these people, right? So it's good to, write tests for my code, but I also need to make sure that I can produce something useful for my colleagues,